Hello. Today I'm going to be explaining the Rust program that I made to generate the Mandelbrot set. So this is what the Mandelbrot set looks like, which is a cool little fractal generated from a equation that plots something on a real and complex plane of numbers. And basically, given any point on this real and complex grid between negative infinity infinity and negative infinity I and positive infinity I is a point, and if we plug that point into our equation, which is z equals z squared plus c, plug that c point into this equation, we want to know if it diverges or if it doesn't diverge, right? If we just run that formula a number of times, does it stay within our localized area or does it diverge? If it diverges, we're not going to plot it, but if it basically doesn't diverge, then we're going to give it a black pixel. So that's what you can see here. To do this in Rust, I'm going to do the same thing, but simply in our console. And basically how long our value stayed within the localized area is going to be equal to how dark that pixel is, or basically the character that I'm going to give it. So let's look at the code. This is how to calculate the value of a given point, and we're going to have to use complex numbers here. So we both z and c are going to be a complex number with a real and imaginary component. In the Mandelbrot series, z starts at 0 and c is what we plug in. For any x and y pixel value, we plug that number in and we calculate the output. And the output is given through this loop here. So we're going to loop through just a random, a set number of iterations. I chose 1000, so it's going to run this 1000 times. And if our z.norm, which is our, if our z value is greater than 2, and the dot norm for a complex value basically means how far away it is from the origin, right? Or from a 0. And so it's kind of like you could use the real components greater than 2 or the imaginary components greater than 2. Both of those work, but this z.norm also works. If it's greater than 2, then we're going to return the number of iterations that it took to hit that point. So the greater number of iterations, then that means the darker the pixel is because it stayed within a local area longer. Or if it shot off really quick to infinity, then we returned sooner, and that's going to be equivalent to a lighter pixel on the screen. And then we return that number of iterations. And so we're going to hit this eventually every time. So this never runs, but we do need to return outside of this for loop. And so we're calculating a point inside of our calculated rows. So we want to run this function on every single pixel within our Mandelbrot. So from this is somewhere around negative 1.5, and this is around 2, I think. And so for each one of these values, we want to calculate it. And you can see that within these are the real number line right here. This would be equivalent to all of our real numbers, and the imaginary plane is our vertical up and down. And so, for example, somewhere around 2.1, it's going to diverge very quickly, and so we get a plus sign instead of an at sign because it diverged quicker. So we need to run this formula on each one of our points, and this is what we have: 2 loops one nested inside the other so that we can iterate over our entire values of x's. For each row, we're going to run the same thing. So we first off, we create this array inside of an array, and we give it, in Rust, you need to give it a capacity. We give it that capacity of our width, and then we do the same for each row with the capacity of our height. And then we iterate through each one of those pixels, which is a broad term here. And then we I forced everything to a float 64 so that we can do a little math on it. Here, these are numbers that I tweaked with to get the Mandelbrot to show up like it is. If I move these values, we're going to get a different section of the Mandelbrot fractal. We could zoom in, we could shift left, we could shift right. I've put it right here because this kind of shows the cliche image that we like to see zoomed out. And then for each one of these pixels, x and y values, we're going to plug that into our calculation, our formula, give it that, like I said, that 1,000 iterations, and then that's going to return our value, the number of iterations it took before it broke, and then we're going to push that number, add it to our array, and then we're going to push that array into our array of arrays here, and then we're going to return that. And here we're going to render this array of arrays, which is just a bunch of values, as characters on our screen. And here's my render function. I grabbed this gradient, this ASCII gradient off the internet, from a supposed light pixel to a dark pixel, and we're going to grab a array from this string, and then we're going to use 2 for loops so we can go through every single value in our array of arrays. In Rust, they're called vectors, I guess. It was the first time using Rust. We're going to then match each character to or each value to a character. And you can see for 0 to 2, we're going to give it this nothing character. If it stayed within the local area longer, less than 2, then we're going to give it this @ sign, so the darker pixel. Or sorry, that's index 8, index 9. Anyway, and then we're going to push that line. We create a line, add all the characters, take that line, and then we print it to the screen. And then we do that for each row. And that is how we end up with a pretty little picture.